The best way to test your understanding of these concepts is to practice. Practice, practice. Analyze as many data sets as you can. Always volunteer to look at somebody's data. Sit over someone's shoulder while they're doing analysis. And most importantly, read as much from the literature as you can. You don't have to skip the methods section anymore when you read papers. In fact, that's the section that you're probably going to read the most closely, the most diligently. Let's look at a few examples from the literature of some paired t-tests. The dean and I always had this idea in obesity research. We wanted to see when people go on cruise ships, how much weight do they gain? We had this idea that when you walk up it's called the gangplank, when you walk up, there would be a little scale and you would stand there and it would weigh you. And then when you came off at the end of the trip, it would stand there and it would weigh you again. How much weight do you gain during a cruise on paired t-test? Then I saw this study. This was the effect of exercise during the holiday season on changes in weight, body comp, and blood pressure. The holiday season, this is from the European Journal of Clinical Nutrition. So we even have to think, what do they mean there by holiday season? In the US, I would say holiday season generally starts from the Monday before Thanksgiving until about, January 3rd. That might not be the same as it is in Europe. But take a look at this. Changes in measured variables from pre to post. So it's a paired sample t-test. And always look at your data, right? Always look very closely. Here's the age. Check to make sure that everyone's age went up during the study. You'd be surprised at the number of mistakes and errors there are in data entry. This study was about body weight. So let's look at the men. The men at the beginning of the pre-holiday season, their average weight was 81 kilograms. At the end, the average weight was 82 kilograms. It went up 1 kilogram, which, as you all know, is 2.2 pounds. Is it a statistically significant increase? Well, we have a little letter there, 0.96. A, if we go down to A, significant change at an alpha level of 0.05. So on the average, you gain a significant amount of weight during the holiday season. And we asked the follow-up question, is it clinically relevant? Yeah, 2 pounds. 2 pounds is nothing, right? I can gain 2 pounds during breakfast. But wait, if you're lucky, how many holiday seasons do you go through in your life as an adult? 40, 50, 60, 2 pounds every time. Now we're talking about some sort of problem. Always think about the clinical relevance when you see statistical significance. And you can look at this data too and see how body fat goes up. You can see how blood pressure goes up, resting heart rate goes up. I always like this one the best. After vacation, what happens to your resting heart rate? Oh, that was a great vacation. I need a vacation to recover. This is a classic paired t-test. I found this study, a student sent this to me a while ago, and it was someone was lamenting that they're having trouble getting their research published. This is kind of proof that you can get really anything published if you do the study. What's better to pull off a Band-Aid, to rip it off or to peel it off slowly? I'm writing this in 2020. I don't know, recording this in 2020. I don't know if this guy's still alive around. His name is Nelly. He used to walk around with a Band-Aid. I'd love to rip this one off fast. Actually, I'd like to rip it off slow. Which one causes more pain? Well, here's a study that tests fast versus slow Band-Aid removal. And what they did, they call this the F bar and the S bar. Always make an abbreviation. It sounds more official. And they took people and they would do each technique on each person. And they would randomly decide which one they were going to do first. And they would do the left and the right. And they would do it on different locations of the body. And here are the results of their study. The mean overall pain score for the ripping it off was 0.92. And the mean pain score for slowly removing it was 1.58. And we see that their p-value is 0.001. Statistically significant evidence that you should just rip it off. Less pain. Now, is it clinically relevant? Well, this is interesting because the difference here is 0.66. And it's 0.66 what? Units? What is a pain score? Well, 0.66 might mean a lot if you say, hey, on a scale of 1 to 5, how much does this hurt? 0.66 is different if you say on a scale of 1 to 10, how much does this hurt? Or on a scale of 1 to 100, how much does this hurt? It doesn't say in this paper. We can't really tell what that scale is. But these researchers include that this represents a highly significant difference of 0.66. When I read that, I was like, wait, what is a highly significant difference? I mean, we taught this game that we set an alpha level, and usually it's 0.05, although there's nothing magical about 0.05. And we said if something was less than alpha, we reject a null and we call it significant. And if something is greater than alpha, we accept the null. Okay, now, what is this highly significant difference? Highly significant. It's either significant or it's not. It's either significant or it's not. So you have to be very careful. The way we do this, if alpha is less than 0.05, it's significant. If it's more than 0.05, it's not. This is one of the greatest websites I've ever seen. This guy went through and somehow through PubMed or Google Scholar, he found all sorts of p-values that were greater than 0.05, and he looked at how did the researchers describe them. They should be described as not significant. But you see that people get very creative in describing their p-values. Suggestively significant. Tantalizingly, this is just dumb. What is this? Trend bordering on just this. Don't do this. Don't do this. If it's less than alpha, it's significant. If it's more than alpha, it's not significant. That's it. Here's a cool example of a paired t-test showing how creative you can get with the study design. This was a study looking at air quality in buses in Hong Kong. And what they did is they put a little thing in the bus cabin that would measure the air quality. And then they also put one outside on the side of the road. And when the bus would drive down this route, when it would drive by one of the outside stations, they would press a button and it would measure the air quality simultaneously inside the bus and outside the bus at the same spot. And then you want to see, is it better to be inside the bus or outside the bus? And what would you pair? What would you pair the data from this spot inside the bus to this spot outside the bus? No, it would be the same spot. And so we can look at this and we can see that it's actually more dangerous when it comes to some of these measures to be in the bus than it is to be outside breathing the exhaust of the bus. I'll show you one more example. This was an example of kids who underwent surgery during epilepsy. Kids with epilepsy who underwent surgery to lower their number of seizures. And the kids were measured on their IQ. They were measured in 3 different things. We can look at this figure here. They were measured in their verbal IQ, what's called the performance IQ, and then this other scale completely unrelated to IQ, which is called the child behavioral checklist. And they were measured before the surgery and after the surgery. You can take a look at the figures. Remember, always look at your data first. What do you see? This is interesting. This is one of the worst figures that I've ever seen in my life. A really important thing when you visualize your data and when you make graphics is you want to think about the ink to information ratio. How much ink am I using to get across my data? And if you look at the size of this screen right now, this entire half of the screen is telling us how much information. Well, there's a number here and a number here, the mean of the verbal IQ pre and post. There's a number here and a number here, and there's a number here. This is 6 numbers. Look how much space or ink they use. Look how much of your attention is required just for these 6 numbers. I mean, look how much space it actually takes. There's 6 numbers right there. They could have used that space. So this is a really bad figure because it's just a waste. It's literally a waste of space. But also, if you think about it, this is a bad figure because how would you really like to see how verbal IQ changed? Well, ideally, you would like to see these kids and you would like to see what their IQ was like before. And then you would like to take them and see what their IQ was like after. And you would like to visualize for each kid, how did those things change? And you would be able to get a sense of whether their IQ went up and down. I just remembered a really good thing when you visualize data. The rule is this: above all else, show the data. Actually show the data. Here, we're hiding the data with these three-dimensional bars and all of this background junk. I would much rather actually see the data themselves. This is not the worst thing on the slide. They did some things nicely. They ran a paired t-test. That's what you're supposed to do, right? You have the pre and the post. One child's IQ measure after should be linked with their IQ measure before. But they did a lot of things that are really dumb here. IQ and this thing, the CBLT, are measured on totally different scales, but they put them on the same graph. That doesn't make any sense. You wouldn't put BMI and blood pressure and height all in the same graph. That doesn't really make any sense. Then when I read it, this actually got a little bit worse. So go to the end of this paragraph. A paired t-test confirmed the lack of significant change. This is really bad to say this word, confirmed. These people are trying to accept the null hypothesis. And remember, if P is less than 0.05, you reject it. P is less than alpha, you reject it. If P is greater than alpha, then you fail to reject it. You never confirm it. But the sentence gets even worse. Confirmed the lack of significant change in intelligence. Look at this right here. P is less than 0.99. I don't know what that means. It could mean P is less than 0.05 and you reject the null. It could mean P is greater than 0.05 and you fail to reject the null. I have no idea how 1, 2, 3, 4, 5, 6, 7 people with all of these degrees after their name and the editors and the reviewers, nobody caught. This is maybe the dumbest thing that I've ever seen. This is mind-blowing to actually see this in print. All right, we'll talk more about p-values, statistical significance, hypothesis testing, study design, and more when we get into looking at continuous data, correlation analysis, and the all-important statistical tool of regression.